Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the third video in the series on understanding capacitance. In the first video, I covered the basic descriptions of how capacitors are built and how they work. In the second video, I covered design-related stuff like series and parallel capacitors, RC time constants, capacitive reactance and impedance, and then real-life capacitors. In this last video in the series, I'm going to dive in just a little deeper into the physics of why and how capacitors work the way they work. It's time for the extra credit portion. Now, if you end up feeling a bit confused at the end of this explanation, you're not alone. I will try to unravel it the best I can, but much of what makes capacitors work seems counterintuitive to us. My first reaction to some of this stuff was like, huh, what? And I had to go back again and again, and with some noodling on it and some time and re-reviewing this stuff, it eventually made sense to me. So hopefully I can take my understanding and help you understand it. Now, let's dive into trying to understand why these physical characteristics about how a capacitor is made makes a difference in the capacitance. First, we have to lay some groundwork in electrostatics. Isn't this fun? Now, let's remember something from the extra credit portion of my video on understanding voltage. Now, here's this lovely equation from that particular portion. We have the charge difference. We have the radius or the distance away. We have the dielectric permittivity. So what makes a difference in the E field around a point charge? Well, if the charge level goes up, the amount of charge we have goes up. It's up here on top. And when that goes up, then the intensity of the electric field goes up. Notice, though, that the distance, this R here, is on the bottom. That means when this gets bigger, this gets smaller. But it doesn't just get bigger, notice that it's squared. So that means if we go from 1 to 2, because this is squared, we have a 1, and then it becomes a 4. So the E field goes down by a factor of 4. It becomes 1/4 by doubling the distance. That is traceable back to this whole spherical aspect of things. So here's my beautiful picture here. Here's our point charge. We have a charged object here. That's our Q difference. And the radius, I have two radiuses outlined here. I have radius 1, I have radius 2. Now, you remember, you have to think of this in 3 dimensions. So this is actually kind of like a slice. So you're seeing the slice of a sphere. But what happens? Here are the electric field lines going out, and they always exit at right angles to the charge. And here we are at radius 1, and notice how far apart these are here. We're right from here to here. They're not very far apart. But now we go out to a larger radius, and you notice how they're diverging as they go out. So it makes good sense that the electric field intensity, as we go away from this charge, goes down more and more and more and more, because you have the same amount of energy, the same stuff. It's just spread a lot thinner over a larger surface area. And the surface area of a sphere, by the way, is 4 times pi times the radius of that sphere squared. And so it makes sense that in this particular case, as you change distance, the E field goes down by the square of the distance. Also notice that the dielectric permittivity associated with the space around this has everything to do with the E field as well. The higher the permittivity, the lower the E field. So that is from our understanding voltage video. Now we have to apply this to a different situation because the capacitors are not designed around a spherical type of symmetry like this. Capacitors are parallel plates, so we have to consider that specific case. Now let's consider what happens to electric field intensity between two parallel flat surfaces. The electric field is confined between the two surfaces. And so we see here our electric field is right here. It's not going anywhere. It is in between these two surfaces. And like I said, the electric field must exit the charged surface at right angles to the charged surface. So if these two plates are perfectly parallel to one another, that means that all of the lines of force, all of the electric field lines are confined between the two plates. There's no diverging. All of the lines are parallel to one another. As a result, the electric field intensity does not change from one point to another between the two plates. It wouldn't matter if you were here, or up here, or down here. The electric field intensity remains exactly the same. The resulting reality is that the electric field intensity E between the two plates does not care how far apart the plates are, unlike with our spherical experience. This doesn't matter anymore when it comes to electric field intensity. Now, let's apply this principle to the idea of our capacitor. Now remember, what is capacitance? Capacitance in farads is equal to charge per volt. I told you this is really important for us to remember. Now, if our plates here have we have a plate here and it has an area A, and we have chunked onto that plate charge Q, then the charge density is going to be equal to Q over A. Okay, so it's coulombs per square meter. Per square meter. All right. Now, without going through all of the math and using Gauss's law and Gaussian surfaces and all that kind of fancy stuff, you're just going to have to accept the following equation as being true. The electric field intensity, E, is going to be the charge density divided by the permittivity. Now, remember, permittivity here is your dielectric constant times the permittivity of free space. That's what this is. So this is coulombs per meter squared divided by the permittivity of the material in between these two places. Now, this right here, just as a point, is 8.854. 4 times 10 to the minus 12 farads per meter, if I remember correctly the units. Now, notice that there is no distance in this equation. It is simply the charge density on the plate, which is coulombs per meter squared, divided by the permittivity. So it tells us that the intensity of the electric field does not depend on the distance between the conductive plates. And here's another equation you're just going to have to accept. Voltage is equal to the electric field intensity times the distance. So, if these two plates are charged with a given charge density, changing the distance between the plates does not change the field intensity between the plates. So, changing the distance between the plates does not change this. However, changing the distance between the plates does change the potential difference as we measure it in voltage. So if the distance between the plates goes down, the potential difference between the plates go down. You say, well, why is that? Remember what the definition of voltage is? If you do 1 joule of work to move a charge between two charged bodies, 1 joule of work over 1 meter, you get 1 volt. And because work is force times distance, the greater the distance, the greater the work. The less the distance, the less the work. That's why voltage here, when the distance goes down, you're doing less work because you're moving less distance, and therefore the potential difference goes down. And so as these plates come closer together, the potential difference between the plates goes down. Even though the charges remain the same, all we've done is change the distance between them. Okay, so let's talk about what happens with the dielectric here. Well, remember the dielectric constant speaks about how easily the material is polarized in the presence of an electric field. So when we stick our dielectric in here, we have, let's say in this case, a positive charge on this conductive plate and a negative charge on this conductive plate. We put our dielectric in there and it polarizes because remember, like charges repel, unlike charges attract. Now, the electrons, the charges in this dielectric, because this is an insulator, are not free to move. But that doesn't mean that the material can't polarize. So what you end up with is one side of the material, in this case, the side closest to the positively charged plate, all gets negatively charged. And the side closest to the negatively charged plate all get positively charged. what this does is it sets up an electric field that opposes the electric field that the plates have. And so the net electric field in the presence of a dielectric that has polarized is equal to the electric field that you would get if there was no dielectric minus the opposing field of the dielectric material itself. So the higher the dielectric constant, the more easily this dielectric is polarized, the higher this opposing electric field is in the dielectric, and the lower the net electric field is here. Now remember, we were just talking a few moments ago, voltage is equal to the electric field, in this case the net electric field, times the distance between the plates. So if we reduce this net electric field by putting in a dielectric with a higher dielectric constant, then what happens to the voltage? If we haven't changed this distance between the plates hasn't changed. But what we have done is we've reduced the net electric field in there with this dielectric, and our voltage has no choice but to go down. Now this is assuming we have not changed the charge. Okay, so in this case here we're saying we've put so much charge on here with no dielectric in here or air as a dielectric. We have one voltage level. We change out this dielectric with one with a higher dielectric constant, which sets up a stronger opposing electric field inside of here. We still haven't changed the charge yet. The net electric field inside of this capacitor now has gone down. The voltage, the potential difference has gone down because the net electric field has gone down. But the distance is the same, the charge is the same, but the net electric field has gone down, so the potential has gone down, the potential difference. Now, going back to the definition of our capacitance, capacitance is equal to charge per volts, coulombs per volts. Now, we're assuming charge has not changed. What has changed? The potential difference has gone down. And because it's on the bottom of this, if this gets smaller, then that one gets bigger. So the bigger the dielectric coefficient, the stronger the opposing electric field, the lower the net electric field, the lower the potential difference. The lower the potential difference, the larger the capacitance. That's how dielectrics work. Now, how does that work out? Well, it turns out that if you have a 100 picofarad capacitor with an air dielectric, which has a dielectric constant of 1, and change all of that air out with a dielectric with a constant of 3, you now have a 300 picofarad capacitor. Now, if you want a more complete explanation of all this with all the equations and the Gaussian surfaces and all that stuff, I would encourage you to watch Dr. Walter Lewin. He's an MIT physics professor available on YouTube, and the link to his video will be on my posting here. He does a fantastic job walking through all of this with wonderful demonstrations I can't even begin to duplicate here. So let's bring it all together. Capacitance is defined as coulombs per volt. If we increase our ability to store charge, then we can increase the capacitance. We do this by increasing the area of the plates that we have available to us. Given a fixed amount of charge on the plates, if we can decrease the potential difference between the plates, then we can increase the capacitance of our capacitor. It's like expanding the diameter of our tank with the same amount of fluid in it. While the volume of the fluid remains the same, the level of the fluid in the tank is going to go down. So we can do that by decreasing this distance between the plates, because voltage is equal to this does not change with distance, but this times distance, the voltage level goes down, the potential goes down, capacitance goes up. We can also do this by changing the net electric field by adding a dielectric with a higher dielectric constant. Now, are you confused yet? Well, I'll tell you. It might take a little noodling. It might take a little bit of time. You might have to go back and listen to this again, do some more thinking about it, whatever it takes. But in the meanwhile, I want to thank you so much for watching. Toodaloots.